So in a pretty short amount of time, we've talked you through machine teaching. We've designed and started to train 4 agents. We've shown you how to download a trained agent system and deploy it in the real world. And this is the power of the Composabl platform.
We call Composabl the intelligence engineering platform, and that word engineering is really important to us at Composabl. We believe that AI should be well engineered, and engineered means modular, flexible, adaptable, explainable, and that's what you're going to see in the platform as we show it to you. Well-engineered AI, and part of that means that what we're going to be showing you is a multi-agent AI system, many AI agents working together to accomplish a complex goal. And agentic AI is really big right now. You're probably hearing it all over the place, AI agents or even multi-agent systems. But here at Composabl, our team has been working with these kinds of multi-agent systems actually since 2017. So it's not a new thing. Our founder and CEO, Kent Anderson, has built personally over 200 of these kinds of multi-agent systems for Fortune 500 companies. And so the platform that you're going to see isn't something that just has been developed really recently based on advances in the past few months. This is something that includes all of the insight and expertise and experience of many years building these kinds of systems for actual application and systems that really do solve these complex business problems. So next slide, please. Thank you. I'm Sarah Cohen. I'm the head of learning here at Composabl, and here also is Justin Johnson. He's going to be your tour guide for most of this presentation. After the introduction is finished, he's going to show you the platform. Next slide, please. So we're starting with the premise that manufacturing has a problem, and it's not just manufacturing, but any kind of industrial business that makes and moves things in the physical world. And there's probably not only one problem, but the problem we're going to focus on today is a problem that these businesses, they run on human skills, human advanced complex decision-making skills of the kind that senior operators develop over years and years of operating a particular machine or a particular process. And those skills are extremely hard to digitize. They're very hard to automate because they're so complex. These operators are funneling years and years of experience, with hundreds and thousands, millions of little interactions with this machine or process into their knowledge. It's very hard to capture that in a set of rules. You wouldn't want a black box AI to do it because the processes are high risk, high value. And you wouldn't want an LLM to do it, or an LLM will struggle because they're not based on text. So this was the case for one of our customers, and we'll tell a little customer story right now. This was a glass, not quite yet. This was a glass manufacturer. Then they had a machine, a very large and complex machine, $1 million machine with 60 control variables. And there was one operator named Alex who was very successful at controlling this machine. He'd been there for about 15 years, and he knew all of the tips and tricks, like when the glass is this color, then you do this. If it makes a sound, a specific sound, then you turn a different knob. All of those insights into how the machine worked meant that when Alex was on shift, there was high product yield. The products were, they were in spec, which is the really important thing for gobs. So they were able to become glass bottles low waste. When anyone else was on shift and Alex was not there, there was a double-digit decrease in the productivity, in the yield. And that's, a really significant difference for a really high-value business problem. So this manufacturer came to us and asked us if we could try to help them to capture these skills, to create a virtual expert operator that could upskill the other workers and provide decision support on this process. So now next slide, please. And we said that this is a great opportunity for a multi-agent AI system. This is exactly the kind of thing where an well-engineered system can help fill the gap and become a virtual operator. So this is what we did. The first thing that we did, we knew that we were going to need data because agents need to train in simulation data that's that's real or realistic. And so we looked at the plant historian data. The engineers at the plant recognized that that data wasn't going to be sufficient because there were situations the agent would need to handle that were not included in that data. So we actually were able to work with them to shut down the plant to do what's called a design of experiments, gather some more data. And then this experimental data plus the historical data, then we worked with machine learning techniques to extend that finite set of real data into an infinite set of realistic situations called a simulation that the multi-agent system could practice in. Then the next thing was working with the engineers and also with Alex. Our team designed 7 or 8 different designs for multi-agent systems. And these are, you can kind of think of it like a sports team. It's different lineups, different combinations of players, different formations on the field, seeing which is going to work best. And the Composabl platform makes that very easy to do quickly, which you're going to see in the demo. So we created 7 or 8, tested them, tweaked, improved, compared to the benchmark, and eventually ended up with one agent that was ready for deployment testing. It passed deployment testing. Alex was actually able to certify it as an expert operator, and it was put into the field to solve this previously unsolvable automation problem. So that's what you're going to see in this demo. Justin's going to take you through an end-to-end process of exactly this, from the beginning of the use case to the end of deployment and every step in between. So I'll turn it over to you now, Justin.
Thanks, Sarah. Why is this not moving forward? Okay. Great. So Composabl is your workbench for building multi-agent systems that make million-dollar decisions. And Sarah's already talked about it a bit, but when you think about what types of they're complex and they optimize the profit margin for high-value systems. And so these agents typically control systems where like just a 1% performance improvement is worth at least $1 million and often more. All 200 of those agents that Kent's designed for these Fortune 500 companies had at least $1 million in ROI. And what I'd like you to think about as we get started is, at your organizations, do you have any systems or processes where a single-digit improvement in KPI would yield $1 million in ROI? And we empower your engineers and operators to build AI expert operators. And as Sarah said, we do this by orchestrating multiple skills together to make decisions that humans would typically make. And this is how we optimize the profit margin. And Composabl is a flexible platform that empowers you to bring the expertise of your most senior operators into the agentic system. And the platform has 2 interfaces. There's the Python SDK over here in the build, and it gives developers and software developers and machine learning engineers the ability to publish any algorithm, machine learning model, LLM, or API that's supported in Python into your agent systems. And the no-code UI is a place for designing agents and using these algorithms and other technologies. And in the demo that I'm going to do, it's a hands-on demo. I'll actually build some of these agents and train them. You're going to see different agents of different designs and in training. And after we train some of these agent systems, I'm going to show you how the agent runtime provides a connector that communicates agent decisions to operate your equipment or processes. So this will be how you can actually deploy these things in the real world. And a quick poll. So we're seeing lots of people talk about agents, and agentic systems are very quickly becoming something that's talked about in the ecosystem. And I'm interested to know, when you hear about agents, what what do you think of? What's the first thing that comes to mind? So we have this poll. You can select more than one. It doesn't have to be just the first one. It could be a combination of things. And also in this poll, what technologies are you most interested in for automation?
Yeah,
What technologies are most crucial for your success at your organizations?
so we'll leave this poll open for another few seconds if we can get anybody else who wants to share what you think of when you think of agents, what kinds of technologies you can use you're interested in using as part of a multi-agent system. Okay, so I'll end the poll, and we've got some interesting results here. We've got LLMs, expert rules and heuristics, and reinforcement learning as key enabling technologies for agents.
And so that's great. We have, multiple things that people are thinking of, and Composabl is an agent orchestration platform. And no matter what technologies matter most to your automation or what technologies you already have in your environment, you can bring those into Composabl, and we enable all of them to work together to make the best possible decision. And our approach to creating intelligent agents is to take your subject matter expertise and combine it with advanced algorithms and AI. And the methodology that we use, that we've designed our whole system around, is called machine teaching. Kent's, who we already mentioned, has actually written a whole book on it, and we're going to talk about it as we build these agent systems. Sarah's going to come in after I've designed some agents and explain a bit about how these agents are designed and why they're performing the way that they are. And machine teaching is a battle-tested, proven way to create well-engineered industrial AI systems. And many of our Fortune 500 customers have built our agents on our platform, agent systems on our platform that have mastered high-value decision, typically made by very senior operators. And if you want to learn more or dig really far into it, he wrote a book called Designing Autonomous AI, and it's available anywhere where you can buy O'Reilly. And here's a reference architecture for agent systems. And you can think of it kind of like this. There are 9 major sections of our brain that each have completely different functions and do completely different things, but they all work together to create human intelligence. In our experience, agents have distinct characteristics that when you incorporate specific layers, they come together to create machine intelligence. And that's why we have the perception layer in our agents. We have a decision layer with skills that take actions, and we have an assistant layer where you can interact in natural language with agents during training. And to further the analogy that Sarah talked about when she was getting us set up here, you can think of it like a sports team. So all of these skill agents, if all of them were goalies in soccer, you'd have a very hard time winning against a team that had strikers and midfielders and defenders. And so you want each of these skill agents to be able to specialize so that the team can come together to make better decisions than if it was just all goalies. And so today, the use case that we're going to be working on is building agent systems to improve the performance of a chemical reactor. And this is just one example of a use case for the Composabl platform. And, it may or may not be relevant to your business, but there's tens of thousands of million-dollar use cases that you can tackle with Composabl. And you likely have hundreds or even thousands of applicable use cases at your organization. So think of this more as an example to spark your imagination, to give you an idea of what you can build on the platform so that you can apply it at your organization. And we have a white paper talking through the use case and our solution, and you can get a link to it in the chat. Sarah's going to drop it in there. And so before I explain the use case in a little more detail so you can understand what these agent systems are doing to control this process, I'm just going to jump straight into the platform and give you an overview of the platform here. So this is Composabl's UI. It's no code. The first thing that you're going to do when you get into Composabl, you can see we have these two projects are example projects that'll be already there where you can see some agents already designed and trained. But you're going to load up a simulator. You can load up a simulator in the no-code UI. We have lots of documentation about how to do it. We have a cluster where you can train that is self-service. It's just a click of a button, but you can also bring your own cluster. We have a Azure Marketplace offering that does all of the work for you, brings in Kubernetes and gets all of the components and spins it up. It's really easy to deploy, but you can also bring in AWS or GCP or even your own in-house compute. And the first thing I'm going to do is show you how to create a project. We have a LLM that'll help you automatically bootstrap your project. What I'll do here is add in some description that I've already created. With this, you're going to say what you're doing here. You're going to explain the process and what the goals are. Then you're going to tell it what each of the skills are you need as an expert operator to manage this process. And then you just name it. We can select our simulator and then add ourselves to a team and create the project. So it's thinking here for a moment. It's understanding what you've typed in, and then it's creating a bootstrap for your project. So we've created 5 skills and some goals. And now you've got some skills over here. To design your first agent, all you need to do is start dragging the skills to the skill layer and then click train. Setting up the project with the LLM isn't perfect. There's still some configuration that you need to do. I'm not going to do that. I've already set up another project that we're going to be working from, so you don't see me tweaking config. But now I'll go back to our deck and then just very briefly talk to you about this use case. So it's a chemical manufacturing process, and temperature control is needed to ensure the quality of the products and the amount of products that you get, so yield. And the agents control the temperature by adjusting the coolant. And this is a manual process today. The expert operator would be watching the whole process and doing these adjustments as the reaction happens to create this product. And as the reaction goes on, the tank heats up. The reaction's too cold, too little product may be produced, or the quality of the product won't be, good enough to sell. And if the reaction runs too hot, something really bad can happen called thermal runaway. And in the worst case scenario, you could actually have an explosion. And if that happens, the reactor is down, you're going to have to replace it. And in the worst case, someone could be injured or actually killed. And so is so mission critical. And these are the types of high value decisions that Composabl is perfect for. Let's see. Great. So these graphs show data from trained agents run 100 different times. So these agents aren't in training, they've actually been trained. And we plot the data from each run to show the variance during different runs at each point in time. On the graphs, you can see there's 3 phases of the reaction. It's starting to heat the tank, ramping up, and then producing product. And the first graph is our benchmark. It shows the results of the company's current solution, which is an MPC controller. And we'll be using that to benchmark against the other agents that we're creating. The y-axis is temperature, the x-axis is the crease in temperature if it was linear, which it's not. The ramping up phase is difficult to control. And the blue represents the spread of temperature from those 100 different results of the controller. And the red line at the top is what we want to pay attention to because that's where we have the potential for thermal runaway. And in real life, the expert operator would make decisions to step in to prevent uh, the uh, the system from getting over that red line. And you can see that each of these different graphs has their own personality, just like each of the people on the floor will have their own personality and abilities. And so we're going to build the other four agents that are attempting to optimize the profit margin. And the chemicals, just to go back to what I said earlier, the chemicals in this process are so expensive that a single digit improvement in yield can be worth more than $1 million. So now I'll jump back into the UI and go to this project that I've already created. And then I'm going to create a skill that is going to control the full process. So we're creating this skill that is using deep reinforcement learning to teach the skill agent, to teach the agent how to operate this by running many, 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 many experiments. I'm going to call this skill control full reaction. So in designing skills, what you're doing is setting a goal, which is what you're trying to achieve. And in this case, we're trying to maximize episodic yield, so to get the most amount of product as possible. Constraints are, you can think of them as things that you don't want to have happen while this process is running. So it could be all different types of things. An example of a car is you want to make sure that the car is actually in the lane. It can't go off the road. That would be very bad. And so you're going to put boundaries that say stay within this area. There's two types of constraints. There's avoid and there's terminate. So in the car analogy, there's this rumble strip on highways in the United States, at least, where if you start to veer off the road, you get this that warns you that things are going very bad. In the case of training, you might want to avoid that. So if that happens, keep training, but you're getting close to a bad situation. And terminate is, okay, you just got off the road. Let's stop this session, stop training. This has gone awry. And here we're going to avoid a temperature of 399 degrees Kelvin to the boundary that our simulation has set of 500 degrees. Because in thermal runaway, it's not that things are going to blow up and be horrible if you get to 400 degrees. It's more that it's a danger zone. And then we have success criteria. So let's say your goal is a destination. As soon as you get to that destination, there's no point in training anymore. So you can end that training session and just move on to the next one. I'll save this skill and go back to the Agent Builder Studio and drag this skill over here. And since this is a single agent system, we've already finished designing this. Now, this isn't using machine teaching. It's more like a deep reinforcement learning benchmark against the MPC benchmark. So I'll go ahead and go over here to train. I'm going to choose the composable cluster. You can set the number of training cycles. Depending on the complexity of the problem, you're going to do somewhere between 1,000 to, in certain use cases, we'll do 50,000 training cycles. Each cycle is a 1,000 episodes. So it's going to iterate, do a bunch of episodes. You can set a number of simulators. So if you have a training that's going to be going for a very long time, you can run simulations in parallel to speed it up. I'm going to say 5, and then we start training. So we have this console output, which is showing you the raw logs from the training data. It's going to take a couple minutes for us to get to the point where training starts because it's spinning up containers in the background. But imagine for a second that this agent's already been trained and we've run our benchmark and we've seen the results that we're going to compare against the benchmark. And Sarah's going to explain what the results were. Let's click here.
Yeah, thank you, Justin. So this plot, this is just a blow up of that plot from the last slide, but it allows you to see the personality of each of these control systems a little better. And what you'll notice with this DRL system is that it adapts well to this first steady state. It is close to the reference line and controlling the temperature well, but it doesn't change its control strategy when the transition starts, when things start to get nonlinear. It kind of continues keeping that temperature really low. And then partway through, it recognizes that something is going on. And there you see that very tall area. That means that it's very inconsistent across the different episodes. It hasn't learned well what works best. And it's still continuing to try different things, even, when it's already when it's supposedly trained to handle this well. You can see even at the end, it's still on many of these runs, it's keeping the temperature too low. And in that last steady state phase, which is where most of the product gets produced. And so the fact that this is too cold during a lot of those runs means that the yield improvement isn't as much as it could be. It's still an 8% improvement yield over the benchmark. So that's a pretty good result, actually. You'd be pretty happy with that. But this shape of this curve allows us to know just from looking at it that we're going to be able to do better if we use machine teaching to decompose the process. The last thing that I want to say also is, so that's on the goal of yield. On the constraint of the thermal runaway, not crossing that 400 threshold, it also isn't performing perfectly there. And it's got this, these series of moments in the middle of the process there where it's very close and it's even crossing the line. So we're going to want to improve on that as well. And so that's what Justin is going to show you in the next designs.
Okay, so we're going to go back into the Agent Builder Studio and work on our next, just rename this here to DRO, our next agent system. And this is going to be using a machine teaching design called the strategy pattern. Say. In this design, we're going to be breaking the agent system into its component parts or states, which is the starting up phase, the transition phase, and then the produce product phase. And I've created 3 agents where we're going to start the process, we're going to transition, and then we're going to produce product. I'm going to drag it over here. And like I did in the first example, we're going to have 3 different agent skills in this bottom skill layer. And when I drop these skills here, you'll see this green diamond. The green diamond is the orchestrator. And the orchestrator is, in this case, using deep reinforcement learning to learn which skill is going to be used to make the right decision depending on the point of the process. And the orchestrator can have its own goals. They might be different from the skills. We have 2 different sequence types, the fixed sequence order and the variable sequence order. The fixed sequence order is saying we need to complete one skill before we go to the others from left to right, and the variable sequence is blended. You can think of it kind of like a kind of funny example is an Etch-a-Sketch, right? An Etch-a-Sketch used to draw, you have 2 different knobbies. The left one is left to right, I believe, and the right one is up and down. And the skills that it takes to make a circle are very different than the skills that it takes to make a triangle or When I was a kid using one, I used to try to make landscapes. I'm sure they weren't very good, but that's a blended sequence. I'm going to introduce a new concept to you here now called scenarios. And scenarios are exactly what they sound like. So I'm going to say start reaction. How are we doing on time? Okay. And we're going to add criteria for this scenario, which is, no, we're going to have refs and temperatures here to help the training. Tref is 311, so the temperature reference is 311, and the concentration reference is 8.56. We'll save that. I'm going to have the transition is really similar to the start phase. It's also 311, and the concentration is 8.57. But the difference here is that we need the transition phase to happen in exactly 22 minutes. And we get sensor data every 30 seconds. So that means that we need to have a count of 22. Now, before I create the last scenario, scenarios are exactly what they sound like. And what they're doing is taking this expertise that you get from your expert operators. So when you're building agentic systems in Composabl, you want to involve your expert operators to understand the nuances of the processes that they're controlling and bring that into the AI system so that it can learn how to control these systems or devices, machines, as well as these operators. And you want to interview more than one operator because these are nuanced processes, and that operators might have slightly different ways that they control the system, but get similar outcomes. So you still get good outcomes, and you want to bake all of those scenarios, all of that knowledge into the process of training. You can think of it kind of like an airplane. When you take off, a pilot needs to know how to fly in snow in really windy conditions, if there's ice, if there's rain. And so if you just train an agent on flying in the best weather or not even taking weather into account, you're not going to have an agent system making good decisions. And this is where you explain all of those scenarios so that the agent can train on them. Then we're going to do produce. And produce has a different reference temperature, which is 373. And concentration. And 373 is the temperature that we want to maintain to produce product and get the best results, the highest yield, and the best quality. So now we'll drop these scenarios here, and we can connect them to each other. In most cases, our customers have at least 100 scenarios, and some of them can be trained independently. They don't rely on other parts of the scenarios, and some of them need to be connected to each other. The scenarios are a path. And so when the agent is trained on this, it needs to make sure that it goes to this next scenario to train. And if you connect them, then you can follow that path. And as I explained in our case, we got to start before we transition to go to produce product. And so we're going to connect these all together. So I'll go back to the agent. I'm going to start the reaction here for the first agent, transition scenario for the second, and produce scenario for the third. We can go here and train. I'll do 50 cycles again. 5 simulators, start training. So you can see here that we're 20 training cycles in. The agent started around this amount of reward. This is the reward curve. and then it quickly started learning. When it starts to flatten out, that means that it has learned something and it's just getting better. It's actually getting less reward here, so we'll want to see this come back up as the training continues. And just like we did with the first agent system, we're going to go back and Sarah's going to walk you through a little bit about what we're seeing. Oops, that is the wrong one. That is not good. Sorry about this, folks.
Yeah, well, I'll start previewing what you're going to see while we're getting there. So you're going to see a plot that's pretty similar to the one that we saw before, but I'm going to ask to draw your attention once we see it to the moment where the first steady state turns into the transition phase. And just to give you a little spoiler, what you're going to see is that unlike in the DRL agent, where the control strategy doesn't change at that point, this strategy pattern agent or multi-agent system, because of the way that the entire task is decomposed between 3 different skill agents that specialize in different parts of the process, it's able to change the control strategy right at the point of transition and start, there we go, start raising the temperature right at the right point. And that's because the orchestrator it's set with the scenarios, it's able to recognize when the new phase starts, and it passes control to the control transition agent within this multi-agent system, and that's able to control the process a little better. Now, the control transition isn't perfect. It still is crossing the thermal runaway threshold, and so we're going to need to add something else to the agent to help, another piece to this design to help with the temperature control constraint. But you'll see that we've got another 2% improvement in yield in our ultimate goal KPI, and that's because of the way that the problem is decomposed.
Great, let's go back to the Agent Builder Studio and get started on our next design. Our next design is also a strategy pattern, but we're going to add another layer to it, and that is the perception layer. So I'll just duplicate this. I'll rename it. Plus, the perception layer is where you bring in new information, extra information that's going to help your agent system make better decisions. And this is often machine learning models. So these are models that you've already trained that are proprietary to your process, or pre-trained models that are going to take the data from the sensors and create something new out of that data. And in our case, it is a machine learning model, and what it's doing is making a prediction about if there's going to be thermal runaway. So we can send that to the agent skills as they're making their decisions. And then it gets that additional piece of information to, hopefully, if it's designed well, improve the decision that it makes. There's other things that you can do. You can bring in third-party data, like ERP data. So this is information that you're not getting from your machines or your process automatically, but it's being created somewhere else. You can bring in LLMs to be able to interact with this agent, either while training or in production. So imagine that the operator, wants to tell the agent system something as the operation is actually happening to create a new and you can create a new variable based on that. I'm going to go ahead and drag this over here. And now this machine learning algorithm is going to take the data as it's flowing through in the simulation. It's going to do its prediction, and then it's going to add it as a sensor variable, as a new sensor variable to the agents to make these predictions. And I'll go ahead and train this to 50 again and 5 simulators. let's see. Start training. Great. Now we have this strategy pattern with perception. Something I'll say about the strategy pattern is that each of these agent skills, including the selector, are trained independently. Now, the selector is the um, orchestrator, so it's going to have awareness of what's happening with all of the various skill agents. But this is important because we've specialized these agent skills, we have better visibility into what the system is actually doing, how it's improving, and where um, different agent skills have potentially issues or need to be tweaked. And this is much better than having a monolithic system because this is a very complex process that has a bunch of different areas and a bunch of different decision types. When you run into issues with a single machine learning algorithm or a single DRL, you often have no visibility into where you need to tweak reward functions or the models or anything like that. And so breaking these systems into their component parts gives us better visibility into what's happening. So again, imagine that this strategy pattern with perception has finished training and we've done our experimentation. And now I'm going to hand it over to Sarah to talk through what we're seeing here.
Yeah, thanks, Justin. So when you look at this plot, you can probably understand exactly what's going on here. These three red lines are indicating where that perceptor was able to, using its predictive model, recognize that the temperature was getting too high, thermal runaway was getting close, passing that information to the decision-making layer of the multi-agent system, and then that layer was able to make an adjustment and bring the temperature down. So you can see we're still at a 10% improvement over the benchmark in terms of yield. This hasn't improved on the goal of yield, but it has added this additional element that keeps the agent compliant with the constraint. And so one of the things that we want you to see here is that this is actually a really good result for an industrial process that's happening at scale. A 10% improvement over the benchmark in yield is a giant improvement that translates directly to the bottom line. This system is doing great on safety as well because it is staying, it's got this element that's very successfully keeping it under the thermal runaway threshold, well under. And this was very straightforward to build this in our platform. The ML model, the predictor, did need to be built, by a data scientist or somebody who knows how to build that externally. But the rest of this agent, these agents were all built extremely quickly with using the composable tools. And that's one of the things that this UI is meant to allow, is to be able to create high performing multi-agent systems with a minimum of programming and time. So we're going to show you another pattern that is arguably even more successful, but potentially a little bit more complex to create.
All right, so we're going to create our fourth and final agent. And this agent's using the plan execute strategy. And before, let me rename it real quick. So plan execute. And before we design this agent, I'm going to go and show you a data science workflow for building skill agents, adding perceptors, and adding selectors. Now, the platform makes it very, very easy to create deep reinforcement learning agents, but we want to bring all of these different technologies. We want to bring in the LLMs that we've custom designed to work on our data. We want to bring in these machine learning algorithms that have, you've spent a ton of time on training to get really, really good results. And we want to bring in ERP data because, in a system where you're managing operations, knowing what's going on with your employees at any given point in time can be really important. And the way that we do that is through a SDK. And we have a SDK and CLI that's just composable. So we want to install it. It's just pip install composable. We have a framework for creating these agents. What we're going to be doing here is publishing a controller that is the MPC. So it's an emulated controller based on the MPC that was actually deployed in the plant. And this is important. This is important because an MPC controller is not trivial to make, right? And you don't want to just throw the baby out with the bathwater. You can use different technologies, including the technologies that you've already deployed in your environments. And that's really important because you don't want to completely get rid of your MPC controller if it's doing a good job. And in the case of, in this case, this case study, the MPC controller is doing a pretty good job. The experts there to control the parts and places where the MPC controller struggles. But we're not here necessarily to replace this MPC controller. So I'm just going to go Composabl, skill, publish, MPC skill group. It's going to think for a second. And we're going to choose our project and or organization rather in our project. And then it will very quickly publish it to the platform. Now you can see that we have this MPC skill group. So this data science workflow is a way to give flexibility to bring all of the different people to the table, the metaphorical table, right? You have your machine learning experts and your process control engineers, and you have your people on the shop floor, and the different people in between that they're bringing their expertise and their knowledge and their skills into the agentic system is going to increase the the abilities of these agents. We have the tools for the people that write code, and then we also have the tools for the people that are going to run these experiments. So in the plan execute design, we're going to, oh, nope, I don't want that one in there first. I want this one. We're going to use deep reinforcement learning to do what it does best, which is learn and make more of like predictions. And then we're going to use the MPC skill group to execute. So when we have the skill group flat, each of the different skills are going to be making decisions that are actions that are going to be done in the real world. In this, we're going to have a decision made by control flow reaction that's going to be passed to the MPC controller to actually execute. And I'm going to say we're going to have 50 training cycles and 5 simulations. We've got all 3 of these agents being trained, and this one is actually finished with the training. And for the last agent, I'm going to pass it off to Sarah again, and she's going to talk about what the results we're seeing are telling us.
Yeah, so here you can see, now that we've looked at all these plots one by one, you can see how good this one is. It's really close, especially underneath the reference line. The transition's still a little harder, but it's, this is the narrowest of all of these areas on any of the plots, and that's because this plan execute pattern, bringing these 2 different control technologies together, does a really great job of controlling this mixer well. And we can see that reflected in the 13% yield. So that's awesome. If you were able to make this and deploy it in your plant, you would have, a really big improvement over what you had before. So this is also a great agent design.
Great. So now we're going to talk about benchmarks, which is comparing how these agents performed based on KPIs and understanding what the potential ROI is for deploying these agents. And this is an important concept because when you create a project, what you're doing is you're creating different agent systems that are experiments, right? You might have no idea which of these designs are going to get you the best results. And so on the Composabl platform, you compare how these different systems perform during training to identify which of the agents you're going to bring to do production testing. Now, I've created a different project where I've already finished training that I'll go to show benchmarks. So in our case, we see here that 3 of the 4 agents in this training didn't pass, and that's okay, because what we're trying to find is the best performing agent. You can see here in these that there's this line, which is the ROI and KPI. We've set our KPI here, and then we get this graph and the performance ranking from best to worst. And I'm going to go and let's see. Let's go back to this one, then go to training. Actually, this isn't quite done with benchmarks, so I'm going to go back to my other one, go to training. So when your agent's done training, you get 3 artifacts. They are the historian, the benchmark, and the inference model. The historian is the raw data from your actual training. And you can use this to do your own analysis. You can load it into, say, for example, Power BI. In the same way, we have the benchmark, which is the raw data from the run of the trained agent to see how it performs against the other agents. And you can download that data and run your own run your own analysis. And the inference model is the actual agent itself. It's called agent.json when you download it, and you use it along with our SDK to create a runtime that you can connect to any system. And I've got a couple examples of that runtime that I'm going to, how are we doing on time? Yeah, we got time. I'm going to give you, so this is an example of historian data that I've loaded into Power BI. We also have a Jupyter Notebook that is kind of like just a bootstrap example of how you can use Jupyter Notebook to interact with the data that we give you. And this is using the agent.json. So we have the model here along with Python. In this case, it's a Flask app. So Flask is a fairly lightweight web framework using Python to create APIs. That's for a backend. And we've initialized the runtime. You can see here from line 16 to line 44 is where we've initialized it. And 16 to 44 has well, I guess this is where we've actually got the object here that's we're going to use in our app. But without the comments and spaces, you can get this running in about 22 lines of code. And then I've created a endpoint here that is predict, where we're going to pass sensor data. And in this case, we'd be connecting, in this case, we're just going to a web page. But in the case of a real world environment, we could be connecting to OPC UA or MQTT, which I have another example app that I've built based on MQTT. And then it's going to get actions. So I've got it running already using Docker. So we containerize these things so that they can be deployed in different environments. And Here we've got all of the variables for the observation. I'm going to click submit and we get an action. So the action here is a number that's between -10 and +10. If it's positive, that means that we want the temperature to go up a little bit. If it's negative, that means we need to lower the temperature. And in this case, 310 is, where we're starting to produce product. Remember, the reference temperature was 311. And so the action is we need to heat this thing up. And if I change the temperature to, say, 425, we're going to get a negative number. If you remember, there's two temperatures that are important. One is 373, which is our production temperature, and then the other is 400, which is where thermal runaway can happen. And so we've -3 is fairly high, and we need to reduce this temperature. The system needs to reduce this temperature. This is available on GitHub. We have an example of Kafka. So if you're streaming a lot of data, Kafka is great because it's really good with streaming data, and it's highly scalable. It's able to horizontally scale pretty linearly. And then we have MQTT, which is commonly used in the IoT environment. It's much more lightweight than compared to like HTTP and TCP. And so when you have low bandwidth, low power environments, MQTT is great. And all three of these are available on our GitHub if you want to kind of dig into the code and see how the runtime is integrated in different environments. So in a pretty short amount of time, we've talked you through machine teaching. We've designed and started to train 4 agents. We've shown you how to download a trained agent system and deploy it in the real world. And this is the power of the Composabl platform. Projects like this usually take a minimum of 6 months to, potentially, 2 years. And Composabl gives you the tool set and ability to create and experiment with agentic systems for very complex, very high value things. And that's what I hope we showed you. So Composabl is available to buy single seats on the Azure Marketplace. The Azure Marketplace is great because you can typically avoid having to create a brand new vendor at your organization, because we have our agreement with Azure that covers through your agreement with Azure. You can also buy Composabl on our website, but regardless of that, we hope that you come to us and want to have a conversation with us about what's going on in your organization and how we could potentially help you. Happy to do a lunch and learn for other people in your organization to bring them in and have a similar experience that's more customized to your environment, to educate other people if that's interesting as well. So without further ado, we're both available via email, Justin@composabl.com, Sarah@composabl.com.